it will become a bit tricky when we try to analyze the running time of merge sort of the merge sort procedure that we just defined. So because compared with insertion sort, the code in merge sort is recursive. And we know that the merge procedure, we know its running time is linear. But the merge sort, it contains recursive calls to itself. So regular technique like analyzing the code line by line is not sufficient to decide the total running time of the procedure. So here we need to use some technique called recurrence equation. Okay, so the recurrence equation is a kind of analysis tool or mathematical tool that will be useful throughout the chapter for divide and conquer algorithms. So it's a useful technique to analyze such a divide and conquer algorithms families. All right, so the basic main idea is to describe the overall running time of a problem, of the original problem of size n, in terms of the running time on smaller problems. Okay, it's a bit of a recursive thinking as well, right? So we use the running time on smaller inputs to describe the running time of problem of bigger size. Okay, and then with the recurrence equation generated or obtained, then we are able to use it. We're able to solve it with mathematical tools. Okay, so usually we use the capital T of n to denote the running time for a problem of size 1. Okay, we already used this before, right? Given the inputs of n elements, we let T of n to denote the running time for solving that problem. And if the problem size is small enough, say it's smaller than some threshold C, okay, C is a constant, then we assume that for those smaller enough problems, we are able to solve it using only constant time. Okay, so thinking of the case of merge sort. In order to sort a input sequence, we divide it in half and further divide the problem until the sequence is short enough that there is only one element in it, and we don't need to solve it anymore. So that input sequence of just one element takes constant time to return. Okay, and also, so we also assume that each time when we divide a problem into subproblems, we suppose that we divide the problem into A subproblems. Okay, so this number could change because in merge sorts we divide the problem into 2 subproblems, but it is not necessarily always 2 division. Okay, we can divide into 3 or 4 or maybe more. Okay, so we can use A here for general purpose here, and also the size of the smaller problems could also vary. Okay, in the most general case, we can assume that the size of the subproblem, the size of the smaller problem is 1/b the size of the original problem. And in the case of merge sort here, B is almost 2 in merge sort, right? Because the left half and the right half is almost one half the size of the original size. And the number of subproblems is also 2. okay? But these numbers can change depending on what the problem is. Okay. So in sometimes A doesn't necessarily equalize B, okay? So now the next step is critical. So now we can use the expression here, the big T or the capital T of N over B, because that's the size of the subproblem, right? N over B is the size of the subproblem. We use T of N over B to denote the time that is needed to solve one subproblem, okay? And because we have A of such subproblems, so the total time is A times T of N over B to solve A of such subproblems, right? That is also a straightforward thinking, right? We divide the original problem into A subproblems, and solving each subproblem takes that many of time. So A times this quantity is the total amount of time to solve all of the subproblems. Okay. All right. So that's the first step of applying recurrence equation technique. All right. So in the case of merge sort, we actually, in the case of any kind of divide and conquer algorithms, we always need to take into consideration of the amount of time to divide and the amount of time to combine. Okay, these are not always the free operations, right? Sometimes to divide the problem needs to cost us some time and the computational resources, and to combine the solutions may also take us extra time. Okay, so we just use some arbitrary functions to denote the amounts. Right? Let's say it takes d of n time to divide into subproblems and c of n time to combine. Okay, so our recurrence equation can be written in this way. Okay, so first, if the problem size is below the threshold, okay, if it's small enough, then we say we can solve it in a constant amount of time. So in those cases, under those conditions, T of n is simply big theta of 1. And this big theta of 1 indicates constant time. And in all the other cases, which are larger subproblems, because we divide the original problem into A smaller problems, and each subproblem takes that amount of time. So the A times T of n over B, that's the cost of solving all the subproblems, okay? And plus D, which is the cost of do the dividing, and C, the cost for combining, okay? So all three parts add together will be the cost for the total for solving the original problem, if that problem is above the threshold. Okay, so this kind of equation can be solved if we know the values of A and B, and we know the exact form of D and C. Oops, sorry. Let me share the screen again. Screen just popped out. Share the screen here. All right. So the equation, the recurrence equation, can actually be solved if we know the values and know the forms of the function. And basically, all kinds of divide and conquer algorithms yield such a form of running time, including our merge sort. So now we look at the equation. We look at the recurrence equation into the context of merge sort. Okay, so we'll do some simplification here. So we assume the original problem size is n. We assume that it is divisible by 2, so that it makes our analysis easier. And we assume that n is a power of 2, so each divide will result in 2 subproblems of exactly n/2 size. Okay, and then we consider the cost of doing the dividing. Okay, because we simply compute the middle point of an array, right? When we compute the middle point Q is P plus R divided by 2. That is a very primitive computation. So in the case of merge sorts, the cost of do the dividing is constant amount of time. And conquer, right? We need to solve 2 subproblems, and the size of each subproblem is n/2. Okay, so which contributes 2 times t of n/2 to the running time. That's the cost of conquering all the subproblems. And combine. We already know that. Okay, so this is the part that we need to know about the merge procedure. The merge sort relies on the merge procedure to do the combination, right? We're given 2 sub-arrays that are already sorted. We need to call the merge procedure to combine the results. So we already know that the merge procedure takes linear running time. It's big theta of n. So we can write the C of n into theta of n. Okay, so that's the cost for combining. So that now that we can rewrite the recurrence equation for merge sort into this form, right? Here there's no A's and B's. There are 2 and 2, right? Big theta of n and big theta of 1, which is constant amount of time. Okay, and it's a much nicer form. Okay. And if we further ignore the lower order term, right? We ignore the constant term here, right? Because it's of lower order, we can ignore it. Then here is the final form for the recurrence equation for merge sort. Yeah. So then we are able. Then we are. Our next goal is to try to get a some analytical solution out of this recurrence equation. Okay.